So my name is Marcin Grzybowski. I'm working for Mutual Knowledge Systems, MUN for short. And I will be talking today about our idea for application, practical application for Lurk, which is additional new backend for our language GLOW, new backend for a compiler. And at the beginning, I will say a few words about our language GLOW, what is GLOW. And GLOW is a domain-specific language for writing dApps. And at the beginning, let's look at syntax of GLOW. This is example smart contract, distributed application written in GLOW. And you can see that syntax is mainly inspired by JavaScript with some additional constructs to specifically address things you need to handle. Okay, so we have these additional annotations to help our compiler generate some code which is usually repetitive and forcing programmer to write the same code every time, in our opinion, leads to lots of errors. So this is the code for simple game between two participants. This is a simple coin flip game. And you can see that at the beginning we have description, we have list of participants. The two participants are playing this game, A and B. Here are parameters of this interaction, wager amount and escrow amount. And at the beginning, participant A is randomly selecting some number. He is creating digest for this number, the commitment, which he is publishing. And this happens with this publish statement. Then he is depositing wager amount together with escrow amount. Then player B is randomly selecting some number. He's publishing that number. Also, is depositing wager amount. And he's published. And at the end of the first part, player A is publishing his number. And then we are XORing the first bit of those numbers. And depending on the result, either A can withdraw all of the funds from contract, or B is withdrawing his winning, and A is getting back his escrow amount. And what is important about GLOW, comparing to writing, in comparison to writing smart contracts, distributed application directly in Bluetooth or on Ethereum, is that GLOW is targeting both participant and consensus code. You don't need to, after you write smart contract, normally you need to write some code so participants can interact with this smart contract. In GLOW, we are writing code once, and both consensus code and participant code is generated from this source. And looking at this, looking at this previous example, for example, those parts we can treat as participant code. So those would be compiled to some code which would run on participant machine. And the rest would be compiled to consensus code. It's important that GLOW is high-level language, meaning that it abstracts away the mundane tasks which are usually parts of developing distributed application. So, for example, after you specify the list of the participants at the beginning of the contract, you can see that above the definition of the interaction, there is this annotation with the list of participants. You can use the name of those participants near those special, everywhere when you can, for example, create some, when you're referring to some transfer of funds or publishing on some variable which was previously local, and you don't need to think about authentication and authorization. Those, you don't need to create multiple methods in the smart contracts, each one authorized for the specific user. Everything will be, all this code will be automatically generated by compiler. And also, since Glow is targeting multiple backends, multiple different blockchains, this code, of course, would vary from platform to platform. And with doing this in high-level language, we can produce this code for different platforms automatically. Also, Glow abstracts transactions, and also transactions in non-native token. So as soon some non-native token is supported by Glow on some platform, you can simply call the transactions, withdrawals, and the deposits like you would use the normal native token from that platform, from that blockchain. So, okay. Also, the very important part of making decentralized application of smart contracts safe is handling the commitments of data. This is also, we also have special construct to aid this. There is verifiably annotation, which you can put before some, when you are defining some variable in participant code, which will ensure that only commitment for this value will be published, and later it will automatically add checks to the consensus code, which will trigger some fallback in the case that, if some participant published different value later, different from the one to which he committed. And here we can see that it's sufficient for developer to add this verify keyword in front of the commitment in the consensus code to generate all those checks. And also our formal and also we are implementing currently formal verification tools. We are integrating our compiler with formal verification tools, which will ensure that whole contract is safe from game theoretic perspective. For example, that escrow amounts is enough to ensure desired level of security, and also that all necessary commitments are made, and also that we are not doing any unnecessary commitments, since all operations on blockchain are really costly. And at the end, you can see that with all those abstractions, the code of the app, the code of smart contract, is much simpler. It's much shorter than similar code, for example, in Plutus. Or so we are thinking that thanks to this, it's much easier to both avoid very simple mistakes like some error during authorization, or more complicated like some game theoretic ill construction of contract, where someone have opportunity to always win the game, or someone is unable to win the game, or we can simply ensure that there's no non-backdoor in the contract. And we like to say that Glow provides security to clarity by abstracting all those details away. And thanks, because with Lurk we are able to construct zk snarks simply by writing Lisp code. In this project, we are creating transpiler for consensus code from Glow to Lurk. And let's first compare how this is very basic description how execution of normal smart contract, normal program in Glow works without Lurk. So simply, as I said, part of the Glow source code is translated into consensus code and part into local code, which is run by participants to participants on their machine to just create calls for consensus. In that usual model, some code is run by, for example, participant A. This code is producing consensus to call, a call to consensus, which is sent to consensus, and then some logic, which is implemented in language specific to consensus, is executing on the blockchain. State of the blockchain is changed. Some transactions are triggered by this consensus code. Then another participant can also run his code, produce new call to some consensus method. There is some execution happens on consensus, and so on. And of course, execution of code on consensus is not cheap. So we want to minimize how much operation should happen of consensus. And that's why we are using Lurk. So in our compiler, Lurk backend for our compiler, instead of translating consensus to, for example, Bluetooth, is generating some Lurk program which can take the state of the current state of the contract of application, get some call or some get new state or some call to change the state, and produce answer if this state transition is allowed by logic of the program, logic of the contract. And by creating both prover and verifier, we can use this prover. Participants are using this prover to create proofs that some transition is the state of contract is correct. For example, that in this state of contract, I should be allowed to withdraw some funds from the contract. And then this call, only the new state of the contract and the proof that this transition is valid and should be allowed is sent to consensus. And consensus don't have all the code for the consensus part of contract. Only the verifier for this specific Lurk program, the specific ZK snark. And after verifying this proof and after verifying that this proof match this call, even without being able to actually run this logic, it can order the transaction. It can do some withdrawal. It can change the state of the call. State of the app. Add something, for example, to list of published values, and this is this can be done in turns. And this is how the logic of contract is implemented using ZK snarks. So. Okay, so we started Glow on Lurk project in March of 22. And we started with formalization of Glow to Lurk in Agda. Our language, we already had the formalization of Glow developed in Agda, which let us make sure, because we are introducing those many levels of abstractions. We have the high-level language, so the semantics is complicated and it differs from backend to backend. So the goal of our formalization of Glow was to make sure that for all those backends, the semantics is the same. That we are not by shielding this complexity from developer, we didn't introduce any errors. And also the issue is that different backends have slightly different capabilities. So for managing those special cases, those edge cases, we thought that it's necessary to introduce some level of formality. And we also embedded Glow in Agda, so you are actually able to write Glow programs using Agda and make sure that, and Agda serves as a kind of interactive environment for developing Glow programs. And because we have, with this formalized semantics, we're also able to formalize the whole transpilation process. So we have a very basic evaluator for Lurk in Agda, and we proved that that code which is outputted by our Glow to Lurk compiler can only result with the same execution paths as Glow programs compiled to different languages. So you can safely deploy the same contract on different backends. Right now, we don't have any platform which supports Lurk, but I know that the Atima is actively working on adding support to Lurk for FVM. So to be able to prototype and test this compiler, we created simulated consensus supporting verification of ZK snark. It's implemented as web server. It also implements very simple account model, so you can create identities, attach some state of the balance to them, and you can deploy Lurk implemented smart contracts on this consensus. So you can deploy pieces of Lurk code and later call this contracts and order some state changes, and each of the state change will be executed only if the state transition verifier allows it. And this simulated consensus is not, it can be even used for different things that Glow. You can create, if you want, you can create a different compiler or even try to write contract directly in the representation which we are using to represent Glow consensus. Oh, and right now this simulated consensus is not actually executing ZK snark, it's just evaluating Lurk using Lurk evaluator, but we think that with Nova proving system we'll be able to run some simple contracts in the near future. With this proof of concept, which we were able to finish a few months ago, we moved to developing actual Lurk-based backend for Glow, meaning that we recently finished building basic compiler infrastructure. So we have code generation part finished, and runtime environment allowing people to interact with our simulated consensus. And actually this runtime environment don't have lots of simulated parts. So we hope that this will be sufficient to interact with. I think that we can say that this is ready to interact with Lurk-based smart contracts once the Lurk will be supported by Falcon Virtual Machine. And since we are, we also developed web interface for to allow. Oh, once again, advance this. Okay, and to allow experimentation with Glow on Lurk and see how the Lurk code, what Lurk code is produced for different smart contracts. We created very simple web interface which both interact with our compiler and with the simulated consensus. And I want to give you a quick demo of this. Let me switch for a moment. Okay, so this is pre-recorded. All of this runs, of course, in browser and is communicating with Glow compiler and with simulated consensus via HTTP calls. And you can see that for the specific contract, it created this Lurk code. And this is not the end code which you are seeing here is specific for this contract. But to allow interpretation, evaluation of this, we also have Glow runtime library written in Lurk, which implements all the constructs from Glow language or necessary infrastructure to implement all of these abstractions. For example, just 2 months ago, we had to implement the integer arithmetics atop of Lurk because it was lacking at the moment, but we are expecting this to be supported by Lurk in the near future. And because of this, the big part of this code is this shared runtime library, we expect that this is some area for optimization where we can improve. Maybe we can have some functional proofs about this. Maybe instead of compiling this runtime library every time from scratch, we can have some functional commitment proofs of this runtime library, and this is the key hope and key way of providing very efficient implementation of those smart contracts. Okay, and now after compiling this into Lurk, we can deploy this. We can, and for each of the role in the contract, because this A and B annotation doesn't describe any particular identity. That is just some participant in the contract. So first, we need to choose identities for those roles. Then we are providing parameters, and from this point we can start deployment, because deployment of the contract is for particular identities and for particular parameters of the contract. We can see the address of the deployed contract and the state ID. And this state ID and the list of values published by participants is the only data which consensus needs to store. Apart, of course, from state transition verifier. Now participants are able to send calls to consensus. and we can see that state ID is changing here. You can see that initially participants initially participant B had 190 balance of 190, and after doing deposit, his account is lower. Yes, and we've done all of the. Yes, and now interaction is done. We are at the final state mark 6, and of course, actual interaction. This is for illustration purposes, mainly for someone who wants to experiment with the compiler. Users, participants of the interactions usually never need to select those calls manually, never need to decide if they want to call deposit, withdraw, or publish. This is the part which is handled by code generated for participant. And we added those options here, so you can try to. We cannot be sure that users, so that participants will always run unmodified code on their sides. So this here we added the ability to make incorrect calls to show that consensus will prevent from exploiting contract and calling something which is not allowed at the moment. As I said, 2 months ago, we started development of actual backend for Glow. Right now, we are working on optimizing this runtime library to more exploit ability of creating functional commitments in Lurk. And also, we are planning to implement authentication and authorization using the Lurk commitments directly, and we are expecting to release this experimental compiler together with this web-based interface for experimenting in the next 2 months. And I invite everyone to try it out yourself and compare how it's to develop the app or smart contracts using Glow to how it's the experience of developing similar contract in on Ethereum or in Plutus, for example. So this is all what I wanted to show you.